We was talking about solid state sensors. And like I said, some people refer to them as transducers, but I think we told y'all that a sensor is a transducer, but a transducer does not have to be a sensor, right? You understand that? So they're not one and the same. And I think the analogy I used was a Ford is a car, but a car don't have to be a Ford. So technically, these are more correctly referred to as sensors. And I need to take off 15. Like I said, that was the previous book. I think it's 8 in your textbook. We looked at thermistors. Everybody okay with thermistors? I mean, this name basically tells you what it does. So, of course, we have problems that it's not linear. So if we're going to get an accurate temperature measurement, resistance measurement that represents the temperature, then we're going to have to either do it electronically or just use a very narrow range, right? The actual thermistor here. So this is it right here. This guy's got the little blue dot. That's the thermistor right there. Of course, it's open to the outside air because this actually measures the temperature in my house. So this is the first digital thermostat that I put on my house. It might still work, I don't know. Huh? In your house, we don't use these to, of course, and this does not, this textbook, I don't think, covers infrared. It don't cover infrared. When we emit heat in the form of light. So we are emitting light, right? But it's in the infrared spectrum, which means we can't watch. We can't see it. And the amount of infrared that you put off is proportional to your temperature. So every day when you come in the front gate, they measure your temperature, but they don't have to make contact with you. That's another advantage of infrared over other types of thermometers and stuff that we use all our life. That we stick up our nose or stick up under our arms and stick it to other places, right? Measure certain things, especially when you're a baby. So infrared, what they're doing is they're actually measuring the amount of infrared light that your body is emitting, which we, like I said, we can't see. So those are electronic sensors. So they're not, we can't just sense infrared without running it through electronics and then analyzing it with electronic circuits. So thermistors, we could use this to measure our body temperature. Why is that? Well, that's not true. We can use it, but it's not accurate over its entire range. But what we get by with is we get by with using it over a very narrow range. So if we use it over a narrow range, it's pretty accurate. So like the body temperature does not vary much, right? You understand that? So, above 105, you don't die anyway. You're below. If you're down in the 80s, you're dead anyway, right? You understand? So most of these electronic sensors that you stick in your mouth, those are probably maybe using thermistors or another device called an RDT. Now the book doesn't cover an RDT because these are, what determines the resistance of a conductor? The resistance of a conductor. That's what determines if it's a conductor. But once we fall into the conductor category, what determines the resistance after that? So nobody knows what determines the resistance of a conductor. That's really, huh? what determines the resistance of a conductor? Everything has resistance, guys. We don't understand. There's nothing that has 0 ohm worth of resistance. There's absolutely nothing that we know of. Even superconductors have some resistance. It's just really, really, really down there. But they do something. They of the 3 things that determines the resistance of a conductor, superconductors have to use one of them. So what determines the resistance of a conductor? What? That's what they're rated in, but that's a resistor. We're talking about a conductor. So every conductor, every known thing has resistance to the flow of electricity. We're talking about conductors. So I come over here, this is a conductor. This conductor right here has a resistance to it. I come over here and have this conductor right here. This has a resistance to it. Which one has the most resistance? Okay, so number 1 is the size. We call it the gauge. It's a round conductor. So that's number 1. So the size of the wire. What's the second thing that determines the resistance of a conductor? What it's made of, yeah. And what's the third thing that covers the resistance of a conductor? Temperature, good. So we take a wire that's got a pretty good resistance, like tungsten or something like that, and we wrap it, and we expose that to temperature. And these guys here are accurate. We call them RDT for resistive, RTD, resistive temperature device. The book doesn't cover these because these are not solid state. These just depend on the conductor varying its watt, varying its resistance with temperature. These guys are these guys right here are really accurate. But the problem is it takes a little while for them to respond. So that's why, so odds are if you're measuring your temperature and sticking that thing in your mouth, how long does it take for it to be there? A little while, right? So that's probably using an RDT. These things are extremely accurate. So usually RDTs, these are used, in your water heater, where it don't vary real fast, but they're very, very accurate. So anybody that's worked on a water heater, you have these rods that stick inside of it. So these RDTs are really accurate. The problem is they're extremely slow. Resistive temperature device. Now that won't be on the test, but this is something you need to know right here. That should be taught in DC. We need to go back and look at our DC because this is where you're first introduced to conductors. But once you set the size, once you set the material, then basically, one more thing, guys. We forgot one more thing. There's 4 things. A big one too. Let me erase this. So there's 4 things. There's one more before temperature. I'm glad I caught that. So 1 is the material. That should be number 1. Made of. 2 would be the size. 3 would be the length. And then 4 would be the temperature. So this is the one I inadvertently left out. Of course, is very, very important. So if you ever look at an ampacity chart for a conductor, it's rated in length for a gauge. It says, okay, 24 gauge would have so many ohms per 1,000 feet. Now, superconductors, what they do is they use other metals, but what they do is they encase these things in liquid hydrogen, which is extremely cold. So what they've done is they've lowered the temperature down extremely cold, which means the resistance of the wire basically goes way down. So you ever heard of superconductors? They still have resistance, but they're down in the milliohms. Photoresistors, everybody okay on those? So these guys vary their resistance with light. Then we looked at the Wheatstone bridge. These are used for any sensor that gives us a resistance output, so we can set a reference, right? We talked about photovoltaic cell, which the commercial name is solar cells. These guys actually produce a voltage that's proportional to light. We talked about Hall effect sensors. These guys sense the strength of a magnetic field. Ultrasonic sensors, we talked about these. These are electronic devices. Basically, they shoot out pulses, and then they measure how long it takes to echo back. Then we looked at basically, talked a little bit operational amplifiers that gives us the ability to set a threshold. Pressure sensors. Now these I just added this morning because I realized they wasn't in here, but these are used all over the place now. These are, and I think I talked about that. These are referred to as proximity. And normally, even though proximity means it's worse, it's when something is at a certain spot. Proximity has become known as, these are our non-contact sensors. So we do have other sensors that sense proximity, but since they have to make contact with what they measure, they have a different name. So this is not in the textbook. These are called capacitive sensors. And of course, capacitive sensors, these work off this formula right here, which you don't need to know. You'll learn this in AC. So this is a constant. This would be, we usually use 6.28. This is the frequency applied to it. And then this is what we call the capacitance. So what we do is these sensors, we apply frequency to them. And then what we're going to do is we're going to adjust what we call the capacitance. Two metal plates separated by an insulator, which we call a dielectric. The amount of capacitance is determined by the size of the plate, the nature of the material of the plate, the distance between the plate, and then what is used as a dielectric. So what we mean is if I got two plates, and they're usually like this, and we put a frequency on them, then they're generating a field out. And then if I bring something into this field, then what I'm doing is I'm changing the dielectric between the two plates, which causes the capacitance to go down, which means the output of the sensor would go up. So what's nice about capacitive sensors is these guys the dielectric can be changed just about by anything. So these guys can sense solid, they can sense liquids, and they can also sense gases, which is pretty neat. Then what we do is we mount them in a case. So we have two types, and then we have, this is what we call unshielded. So when it radiates its field, this comes out all on the side, and then we have what we call a shielded. When it radiates its field, it will come out like this. So shielded are more selective sensors. So unshielded has a wider range of sensing, and shielded has a smaller range. Also, unshielded can be mounted flush. So you'll see these used a lot, like on conveyors and stuff, that's mounted up in there, and it'll be a flush. We can mount these flush. Questions? So these guys, they changed the capacitance. That's okay. What you need to know is if it's a capacitance sensor, then these guys can sense a lot. They can sense a lot. Solid, liquids, and gas. The next type of sensor we have, and you can't tell by the look of them, by the way, is these show a gray, and this right here shows a blue, but that's a gray on the side. So looking at the sensor, you can't tell. The part number would not tell you what it is either, I don't think. The part number would, but it's not. I don't think it's labeled actually on the sensor what type of sensor it is. The other one we have is an inductive sensor. These things basically only can sense metal. So inductive, an electronic conductor loop is many coils. The amount of inductance is determined by the number of conductor loops, which we don't change that. The proximity of the loops, which we don't change that. The ferrous metals that the loops are pulled around are placed in close proximity. So these guys right here, basically, all they can sense is metal. The more ferrous the metal is, the further away it would be. These guys they can sense aluminum, but the aluminum has to be basically right up against the surface of it. So we can make these things switch, or we can make them discrete or digital sensors, or we could actually use these things to try to figure out what type of metal is actually in contact with. And then we're back into the book. So we'll go over there at the manufacturer line, and we'll look at these and see where all these different types of sensors are. So we were in light emitting diodes, and we looked a little bit about that. This is not important though, but the problem is that when you look at the rating of a diode, it's going to be given in what we call a wavelength. When it moves down, this is moving toward red. When it moves up, this is moving toward purple. I might have it backwards. Very high frequencies are usually given in wavelengths. We don't need to know that. We don't need to know this. Well, what we need to know is over here, the light emitting diode. So anytime we have a p-n junction and these electrons and holes collide with each other, then what that does is that produces photons, what we call photons. Light, yeah. Sometimes it's in the visible spectrum, sometimes it's not. The problem with silicone is that this guy takes very little energy to cause conduction. We don't have very many photons. And then they come out at a wavelength that we can't see. So light emitting diodes are going to be basically gallium is the main substrate, and then we dope it with other types of material to determine the color. So like we said, so this right here this guy right here would emit a red light. So this is a light emitting diode. This is and these things come in all shapes and sizes, guys. These are just very, very popular. And of course, to turn it on, we need to forward bias it. So one of these leads is the anode, and one of these leads are the cathode. We have two ways of identifying it. Is that notice the leads are at a different length, and the short lead is the cathode. Also, if this will show up, it probably won't, but I gotta know if I can hand them out. There's a little ring that runs across the bottom, And when you look, one at the ring, it's got a flat side. So that flat side lines up with the cathode also. So this LED glows red, and then they come up, and then they enhance the color with putting a colored lens on it. And then we have different types of lenses. By the way, this is another type. This is the lens itself is just a square, but you'll see one side is shorter than the other. Now this one has no additional mark that identifies the cathode. So this is one of those things that you'll have to, if you're going to cut the leads off, you're going to have to pay attention to which one is short. I'm not going to pass this around, but this is a small one. These things can be extremely small compared to this guy. These are the ones I'm passing around. And then the other day I showed y'all 770. But the hard thing is, one of those most probably so y'all see the cathode, if you turn up and look at it from the top, see one, you see a flat side. You see a flat side, and that identifies the cathode. Now these things have a VL. Rule of thumb is around 2 volts. Of course, what you really need to do, so here's VF of V. You notice they actually run from 1.5 all the way up to 2.6. And then also this gives us the intensity of the LED. And then, of course, another thing it gives us is, it gives us the actual current. And then, of course, this shows us the different materials. So right now we have LEDs. From when I got this slide, I'm not even saying that. We got LEDs that run from a gray all the way up to a white. And like originally we said, there was very few colors over time. So we looked at 7-segment displays. The VF of an LED is typically 2 volts at a current of around 15 milliamps. This is if you don't know. If available, refer to the LED data sheet for VF and IF max. And operating in a circuit with a voltage greater than the LED's rated VF, a series dropping resistor is required. LEDs have a very low PIV rating, 4 to 7 volts. So we can't use these suckers as diodes. Odds are if you reverse bias them, they're going to pop off. Very low PIV rating. A rectifier diode with a high PIV rating should be placed in series with the application. So what they're saying, if I've got an LED, let's say I want to put AC on it. Let's say I want to put 120 volts AC. And then I come over here and I have my LED, it would pop right off the bat, but we could come up here and actually put a regular silicon diode in here that had a PIV rating, let's say 300 volts. And then we could come over here and we could put our LED in series with it. And then of course we'd still have to have a resistor to drop a lot of voltage. So this guy right here would have to drop P, but this right here would be, so this would be just a regular rectifier diode that we can hook in series with it so we can operate this in an AC circuit. That makes sense? And we're probably always going to have a resistor that we would calculate to drop the voltage at 15 milliamps. So we'd have that thing, we're cutting off half of it, so what size resistor would I use? Like, tell me how to come about figuring that out. Yeah, but we got to use, well, Watt's law. I have to use Watt's law to calculate the wattage rating. First of all, we're going to calculate the size. First of all, we have to calculate the DC. This is half load rectified, so I take 120, I divide by 0.707. Gives me VT, right? Plus, let's don't do it that way. This is halfway. So let's say 120 times 0.45. Because this is rough. This is close enough where we don't have to worry about the diode drop. So we want this guy right here. If we want to drop 52 volts at 15 milliamps. Is that right? My calculator. Just check that. And then minus 2 volts for the diode, right? Is that the way we calculate off? Is that the way we calculate? It just sounded like he was asking a question. Is that a standard resistor? We got a 3.6, so we use a 3.6. We use around this guy. Yeah, that's why I said we just round up. Makes sense. And we'd have to use a 1 watt resistor. So what we're saying is that being careful, we can come up here and actually have this thing blocked at 170 volts because, and that's VP, guys. So 120, that means 170 volts would try to reversed biased that one, but we got this guy right here that's got a VL, got a PIV of 300 volts. So you'll see LEDs used on power supplies. You'll see LEDs used, even though you know it's well above the PIV rating of the diode. We can put a diode, just a standard rectifier diode in series with it. The guy's only going to see halfway, but that's the thing. Well, these things have very low PIV ratings, and of course we know if we break over that reverse breakover voltage, they're going to go out. So calculating the series resistor, we just looked at that. We looked at 7-segment displays, common anode, common cathode. Do y'all understand those? These guys have been around so long, and we deal with digital so much that we have integrated circuits that we can put in a binary number and it'll actually code it. So one of them is a 7447. This is a common anode driver. And then we have a 7448. This is a common cathode driver. So the 7447 provides a common. So what we'd have to do, so that means this is what we call a common anode. They usually have two outputs on it. I passed these around to y'all the other day. And then what we would do for each resistor, we would come over here and for each LED, we'd put a resistor in here. And then we would connect it to the output. If this was the A segment, we would connect it to the A output of the 7447. And then on the inputs, we have inputs called A, B, C, and D. And what we would do, if you put that in there, it would automatically turn on the F segment, turn on the A segment, the E segment, the D, C, and the D, and display a 0. So it decodes for you. If I came up and put in this one, which is a binary 1, then it would turn on the B segment and the C segment. If I came over and put in a binary 2, it would automatically decode that to turn on which segment you want to turn on. This is a This is not like, well, I just remembered I had these. So I can't pass this around. This is 7. But it's made out of just a lot of LEDs hooked up into the right. This is the A segment, B segment, C segment, D segment, E segment, F segment, and G segment. And then we put power across it right here. And then this would be the difference. So, I need to figure out, I don't remember if we put a 1, if we put a high or low on these. A, B, C, D, E, F, G. So what we'd have to do is we'd have to control each one of these individual segments to turn it on. So if this needs lows to turn it on, which means zeros or common, then I could use a 7447 to run this. If it needed highs to turn them on, then I would use 7448. These are bipolar junction transistors, and we'll talk about those. That's our next big lecture. That's used to actually control each segment. I'll see this. Oh, this is a common cathode. So we'd have to use a 7448. It's actually written on the side. There. So this would be something where, you would use on a display that you had to use numbers on. So common cathode, common anode, everybody okay with those? That makes sense? display, we talked a little bit about this. And actually, I put my, in fact, it's still up here and let you look at it. So images, we use a lot of LEDs. Uh, we group them in what we refer to, technically we call them a triode. This is a group of a red, green, and blue element, but black, these are on a black background. So these four colors, we can display any color we want to. A pixel, y'all heard of that before. Pixel element, these are triads controlled as a unit. All the triads in the pixel will be the same color. Pixel resolution, this is the size of the pixel which determines the sharpness of the image. So the higher your pixel resolution, they used to give color TVs, that's what they were rated in, 1024 by 768 or something like that. That's the way the TVs were actually rated. Now they say like 4K, so they don't actually give us the pixel resolution on some of these high definition TVs. And I think I brought y'all up and they y'all look through the microphone, yeah, and y'all could actually see the triads. So what we're seeing is red, green, blue, but they're so small that our eyes do it just blends them together. Yeah, so when you go over here, I think you go to screen resolution. This is where you're actually setting your pixel size. So right now I'm setting my pixel size to 1366 by 768. Since we display in a rectangle, then that means I have 1368 resolution, 1366 across this way, and I have 768 on this way. Now how many triads that is, I don't know. But the best your monitor would do, so that's the best this guy here would do. I can lower the pixel resolution, but I can't get it even higher. So now, odds are this is one triad per pixel, and that's the best you can do. The problem is on computers, the higher you make your pixel resolution, the slower your computer's going to run. Because, especially games, yeah. So the lower you can make it, it's not as sharp as it would, but your computer will actually run that. So this is, and then of course I don't see the color resolution on this. We'll probably have to find it somewhere else. So that's for this model display right here. Of course, this shows you the big old Jumbotron displays that they have, and they're nothing but just high intensity LEDs or active lights. Not in text. Special purpose diodes is leakage current. These are photodiodes. This is not in the textbook, but just important to understand. Special purpose diodes is leakage current is controlled by the amount of light striking the P-N junction. We place these similar to the Zener. We place these into a circuit reverse bias. As the intensity light goes up, a photodiode's leakage current goes up. So this is a symbol. This is a symbol they're showing. So they're showing the lambda, which is the symbol for wavelength, by the way. Most of the time, you'll see these things drawn. So this is the symbol of an LED. And then this would be a symbol. This is the symbol you'll see most often used for photodiodes. Can y'all see the difference? So one of them, the arrows are pointing out. The other ones, the arrows are pointing in. So we place these guys in the circuit reverse bias, and as the light intensity goes up, the leakage current goes up. and then we could run that through a resistor, and we could use that to measure light. I don't, nobody, I can't find my remote for my measure. So this is basically sorta, this could be, so you got the remote from your TV, and then it's got a infrared LED in it. So when you press these buttons, they flash. And then over here inside my projector, it might have, and odds are it don't, but it's going to be close to it. Over here it might have a photodiode. Guys, I wish I could. This gives us the ability to sense light. Typical photodiode circuit. So basically, the diode varies its resistance. It's like, so we have to put a zinc, we have to put a resistor in there to actually convert it over to a voltage. Other photoelectric devices, PIN device, phototransistors. This is used more often now than these photodiodes. The problem we have with a photodiode is we can't get any work out of it. It doesn't give us a lot of current. So we'll look at a device. We'll try to start in it today. I'll call a phototransistor. These are the guys that's usually used right here. Optical coupler, optical interrupter. We have light activated silicon control rectifiers, which we'll talk about later on. And then a photo triac. We'll talk about these other special purposes. This triac is a name. It's not an acronym, by the way. And we'll look at these when we get into special purposes. When we get into bipolar junction transistors, we'll talk a little more about the photo transistor. These are our photoelectric sensors, and these are in the textbook. We'll look at those on the line. So what we do is we know light does a lot of things for us. So notice what we're doing here is over here we have a light source, which right now could be a light emitting diode. And then over here we have a receiver, which could be a photodiode. So right now, the output of, this is the receiver. So right now the output of the receiver would be true, which means if it outputs 24 volts, right now, out of this thing, I would get plus 24 volts. And when the object comes over here, what does it do? Yeah, it blocks it, and it would make the output false. Yeah. Huh? Well, it would be whatever we want to do with that true, false, true, false, true, false. You're right. We could bring that into an electronic counter that would actually count for us. It could mean that we got a portion. We could use it for. We could time it, and if the boxes are moving at a certain speed, we could figure out if a box was missing. If it was missing a block. We could figure out if it's at a certain position. So if I came over here and like I had a stamp machine that's going to put a label on it or something, then every time it broke it, I'd stop and then I would put the thing on there. So we can use it for a lot of times. All we're trying to do is use this thing to figure out when a device is at a certain spot. And this is why these are called proximity sensors. But they don't have to make contact with what they're trying to figure out is where it's at a position. So the first one we'll look at is exactly one we call these through the beam sensors. So these things start out true, and then if an object moves, it breaks the beam. Everybody okay on those? So that's the name of this. Then we have what we call a retroreflective. So what we do is we have the problem with through the beam is the alignment has to be pretty precise. Because we're going to use a narrow beam light, we're not going to use a light that's big, because if we did, that would change the resolution of it. So you're going to have to align these things pretty precisely before they work. Well, we have these devices called retroreflect. So normally, if I've got a reflective surface, if I bring a light beam like this, then it's going to bounce off at the same angle. So the angle of reflection is equal to the angle of, I think they call it indentation. So that means if I'm over here looking at a mirror, I can't see myself unless I get in front of it, right? You understand? Well, a retroreflector, these things are made up either of glass beads or they're made up of triangles. If I looked at it from the top, it would look like this. And so what happens with this, if I come in from the side, it bounces back toward me, right? You understand that? So retroreflectors, we have a regular transmitter. And then it would be sending out light. And then it hits the retroreflector, and then the retroreflector bounces back. But the transmitter might be skewed a little bit. And then when it hit the reflectors, it would still come back. A good example, they use these little beads in the stripes on a lot of the roads. So even though you're driving, you can actually see it reflecting back to you. They use them on like stop signs on the side of the road. These vests that bicycle people, they wear them. You're over here, and they're over here, right? You understand? But it bounces back what? Bounces back to you until you get past a certain angle, and then you can't see it. They got a retroreflector on the moon. So they can actually shoot a laser beam up there, and it don't have to be aligned perfectly, and it can come back, right? You understand that? So retroreflectors, these guys they don't have to be aligned perfectly. If you take the sensor class, the AET-232, we use one of these, and we have you start walking back, and you don't have to align it correctly. It'll pick you up back good grace of 6 or 7 feet. The advantage of a through the beam is, one thing, they're more selective, and also the distance can be further. So if you use the same wattage transmitter, then the retroreflector, it's got to do what? It's got to go back and reflect off the reflector and reflect back. But it works exactly the same. If there's not an object breaking the beam, then this guy will give us a true output, and if it breaks the beam, we'll get a false. Everybody understand that? So the advantage of a retroreflector is your transmitter and your receiver does not have to be aligned perfectly. So they're easier to align. Then the last one we'll look at is called a diffuse sensor. This actually depends on light reflecting off the object itself. So these basically will give you, we'll have to set a threshold on these, by the way, because these, so black, you'd have to be closer to a black surface, right, to understand, than a bright. So these guys actually flash off the device itself, or bounce back off the device itself. Then we have, we run into these all over the place. I have to change these on manufacturing on it. So these are basically just through the beam sensors. So we 2. We have 4 leads coming out the bottom. This is labeled D for detector. This is labeled E for emitter. And it shows one of them's labeled, so if I'm looking at it from the top. What's going on with the pen? So this has got a plus up here, and it's got an E right there. It's got a plus down here, and it's got a D right here. A D, not an O. So this is the emitter of light. This is the detector. And so what we would do, it's up to you, the way you do this. But basically, I would come over here on my emitter and, no, good question. And I'd put a resistor, and then I would come over here. This would be my photodiode, so this would be the emitter. And then I'd come over here on the other side, and right now they got it drawn as a photo transistor, which I said we'll talk about that later. Right now I'll use a photodiode. This would be the detector. This is the plus, and this would be the plus. And this would be the this, and this right here would be this, right? And then this is connected common, and then I would take my output off right here, off the detector, which we're doing the same thing except they're using a photodiode. So what happens is that when I come over here and something moves through this slot right here, it'll break the beam. So it'll break the beam between the emitter and the detector. I'll put this on a sanitary wipe and we can pass it around that way. So here's my 4 leads. This is the detector. This is the emitter. And you see the plus is on there pretty good. Yeah. And then what happens when an object moves between the blades, when it breaks the beam between these slots right here, then the output would go false. Right? When it breaks the beam, then the output would change state. Let's rephrase that because this is going to be a little different. So let me put this on a center light. Pass around with they'll see it. The name of the device. But the gap is fixed between the detector and the emitter. The gap is fixed. And this is usually used, anybody got a inkjet printer at home? And it uses, to move the carriage back and forth, it's got to be able to find a reference. A lot of times they use a special motor called a stepping motor. And what happens, you ever turned it on, you hear it it'll always go back to the what? To the left. And it's usually hitting an optical interrupter on the left-hand side that sets up a zero. So now it knows its position, and then from that on, it knows where it's at. On the line over there, we'll show y'all this, is that we got a little gantry robot, and it's got to drop, it's going to drop a part into 4 different magazines. And what we've got is these little rubber tabs sticking up, and then they got an optical interrupter inside the carriage where we can align it with the different slots. And like I said, we'll go over there and look, and we'll show y'all these on the AMPRO line. So every one of these sensors that we've gone over so far are on our manufacturing lines over there. This one, I don't think this is covered in the textbook, but it's nice to know. These are liquid crystal displays. So these guys don't produce light, they control light. So in the old days, on a LCD screen, we backlit this with a fluorescent bulb. And we had one fluorescent bulb that backlit the whole thing. So when the fluorescent bulb went out, your whole display went out. So under this, we got some planar monitors, and they're all under here. And these are all, you can see they're pretty wide. They're pretty wide because they use a fluorescent bulb to control the liquid crystal. But the way the liquid crystal works is that we have polarized lens on both sides. So we backlight it with something. Then the light comes through here, and this light's going in all directions. Then we run it through a polarizing lens that makes it go in one direction. And then at the top, we have another polarizer that's set in the opposite direction. So what happens is originally we come up here, and the light does not pass through. And then up here would be a colored lens. So up here, this is where we have either be what? It'll either be red, green, or blue. Now when you take the AC off, then what happens is the liquid crystal it goes in the helical scheme. And what happens is that we polarize it, but what it does now is it follows the liquid crystal and it twists around. And now it's able to come out of the other one, which is 90 degrees out, and now we're able to see it light up. So that's what this display uses. That's what we're using up here. That's what your cell phone is using. That's everything we're doing. We're using what's called liquid crystal display. What they've done is we've got away from big fluorescent bulbs, and we've gone to LEDs. So what they do now, they have thousands of LEDs behind the liquid crystal. So now if an LED goes, that one LED goes out, odds are you won't notice it. If a group goes out, you might have a little dark display on your screen. We don't call them LCD screens anymore. We call them LED screens, but they're still liquid crystal. It's just now they're backlit with LEDs. And what has happened to the thickness of these things now? Now they're extremely thin, right? So this is what we're using liquid crystals, and this is really, really neat. And then above each sail, we would have a little colored lens up there, which would be red, green, or blue. These are touch screens. These are not covered in your textbook. These guys technically use resistive touch screens. These are very popular in industry because so if I had on a pair of gloves, what would happen with me and my cell phone? Well, you can buy the special tip gloves, but just it doesn't go through. So this is why in industry, a lot of guys wear gloves. I mean, the next display we'll look at, which is what your cell phone uses, use these resistive touchscreens. So basically, we got thousands of little cells like this, and they're arranged in a matrix like this. And when I come up here and touch, then what we're doing is we're creating a spot between an X and Y axis. And then the touch screen does this. But these you have to push in on. You just can't come up and do what? Tap them with your finger. You have to push in on. These are very, very popular in industry because a lot of people in the industry use gloves. This is what we use. We use a capacitive touch screen. So this is a capacitive sensor, guys. That's all it is. And we're still setting up a matrix of rows and columns. What happens when you touch this, you're doing that kind of stuff, and it calculates where in the processor inside your phone calculates it. But you just barely touch these, right? You understand? And it picks you up real easy. These are nothing but thousands of little capacitive sensors inside your touch. So my cell phone uses a capacitive touch screen, but I've even got a plastic shell between mine. So this is plastic. It guards my phone, right? This is an Autobox phone. 5S, I'm proud of it. And how often did I talk to Siri on this thing? Never. So I can't even trade mine in anymore. But it's got an Autobox, but I can, even through this plastic, I can do what? I can still set up that capacitive tech that these guys are, which is pretty good. I would still probably have my iPhone 3 if I didn't go swimming in it one day. So anyway. So guys, that's it. That's a couple things we talked about that's not in the textbook, but we're going to go over there and look at the manufacturing line and look at all the sensors that lets that sucker know what's going on. Yeah, it should be up there. The only thing that I think I've added is yeah. So I just added this morning. The inductive sensors and why I added it, because like I said, after I get back off break, we'll go over there and look at the manufacturing lines. And maybe this, if you got a manufacturing line at your facility where you go work, then you'll see all these sensors. Another problem we have with these optical sensors is these guys have got to be in a pretty fairly clean environment, right? You understand that? Capacitive sensors and inductive sensors don't care. Optical sensors, though, this is one of the jobs. I see guys who says, yeah, that's one of our jobs. We have to go around every once in a while and clean all these lenses out. So anyway. All right, guys, I'll take a 10-minute break and we'll come back and we'll go back and look at the manufacturing line. Yes. Okay. Oh yeah. They just don't count toward the assignment. So that assignment PT 2, that's graded in students. You can't read this.
So you can't do this really.
Not on the assignment. That assignment is set on a 2 days. You can't do it now.